start the chapter 6, the producing designs. And we are covering the textbook 1, and then among 8 chapters, now we are starting to chapter 6. So let me say again, the representation is first, and then after we get the knowledge base and also design model, then we can manipulate that representation, knowledge base, to reasoning or other operations. And then the others are applications, interpretation, producing, and also the process itself will be chapter 7. And then chapter 8 will be the future direction, but this book is already 16 years ago, so we'll see what they expected at that time. And chapter 6 is made of 6 sections, and I will cover section 1 and section 2. So issues, every chapter has an issues section, goal satisfaction, and then section 2 is about producing design and through interpretive knowledge. And the others will be covered by Tahir. So there are 2 approaches to producing designs: goal-directed or generative. So we started from design requirement. And the other one is just generate and test model, only using grammatical rules. They use grammatical syntax to produce only syntactically correct sentences. So goal-directed approach or semantic approach. We start from end goal, status, meaning, or performance. So given, or you are given, or starting from a set of intended performances, intended goal, status, design requirement, same wording, intended performance, final goal, right? Best-selling smartphone at Indian ladies, among Indian ladies, young ladies. That is the intended performance. Of the design, we try to derive a description of the design. Description means CAD model or drawing for which can be used for production of the smartphone. And in that process, we need to use interpretive knowledge. And then this approach usually involves excessive refinement or successive elimination, something, through a decompositional hierarchy of goals. So that can be a goal decomposition. We already see that what is goal decomposition, a hierarchy or tree-like, and resolution of the inevitable. There is some kind of conflict among sub-goals. So tree-like structure, goal decomposition, and then among sub-goals, between them, there can be a conflict. Possible, not always, but possible conflict. The other one approach is a generative approach or syntactic approach. So the grammatical rules are used, right? And also sometimes prototype description is used. But here, evaluation is more important than before. Comparing performances. Evaluation itself is, we say, comparison between performances. Good, bad, fast, or cheaper, expensive, lighter, heavier, and propose a design description only using syntactical or generative grammatical rules. And then interpret it. Interpret it means similar to evaluation, evaluating its performance. And then propose a new design description in response to evaluation. That is the cycling of design. Right. We see this slide several times. So in this way, this is a semantic approach when we start from intended performances and use interpretive knowledge backward to arrive at some kind of design description, alternative design. So we call this is abduction. The other one is syntactic approach is just using generative knowledge to produce any design that is correct. So finally, we need to find out this intersection area, which satisfy both intended performance and also grammatical rules. So there are some issues in goal satisfaction. There's a problem of closed word assumption, and also conflict resolution, conflict among sub-goals, and one-to-many mappings. And that is problems we are facing. And deductive rules usually apply in this process that when the form is given, we can interpret or deduct or predict its function of that form or shape. Right? And also explicit description is given, we can find out the implicit meaning of that description. Right? Meaning here, or performance of that. That is usually coming with the design system, engineering system. Condition and find out symptoms is medical or diagnosis of operation of any machine. And event is given. We may find the evidence of this. That is, we use deduction. And one of the issue is closed word assumption. When we turn deduction to abduction, so in reverse way, there may be other ways that satisfy preconditions, the intended performance. Right? When I said several times, deduction, always there is one single answer, right? Correct answer about this question, right? About this question. When I apply 10 kilometers over there is a single correct answer there, break or not break. But we don't know until we have enough knowledge of analysis. Right? But if it is reversed way, when we apply 10 kilogram force on it, I want to design a pipe cylinder that is not breaking, sustaining that load. Then there is not single correct answer. There can be different optional answers can be produced. That is the way, right? This is saying this. So closed word assumption means there is only one single mapping. There is a usually say closed word assumptions, but this is not working in design world. Right? So deductive rules again. Motor is connected to wheels by drive shaft, then energy of the motor will be transferred to wheels. There is deduction is there is a single correct answer, but the other reverse way is not. Room is air conditioned, then will be cool in summer. But there are the other ways to making this room cooler. And garden design is based on the geometry of platonic solid shape, special shape, then garden will appeal to the intellectual some people. That is a deduction, but abduction is different. A implies B and C implies B. So in this way, there is a single way, but the other way there can be a multiple answer. Sometimes it happens, but this is the reverse slide coming from previous ones. This is general terminology, but in design world, this is starting point of design requirement, same as the reverse way of. And another issue on producing designs is conflict resolution among subgoals sometimes. Set of statement may appear consistent as deductive rules when we applying deduction. But when we translate into abduction form, they may be lead to contradiction. May, not always, may. So sharp teeth and no sharp edges is requirement for next problem. Then we can arrive at different. So this is example of inference. Inference net means reasoning a network for a carpenter's tool. The requirement that we want to make a carpenter tool which satisfy. We need to cut wood with this tool, but still we want to have a safe tools together. So that can be a contradicting requirement. So to cut a wood, we need to have a steel material, and also we need a sharp teeth, but that can be arranged appropriate. For the safety, we need to have no sharp edges, but this can be sometimes contradicting. But anyway, we need to develop such a device. So same one is abstracted as an inference network. So you can see that this is contradicting requirement for this purpose. Anyway, we need to arrive at some solutions. And then there is some picture, I guess. Right, this one. It should be, the order should be changed. Anyway, so there can be some souls that satisfy the rule, depending on the situation. But it looks to me it's more safer for me than the others. But depending on the situation. All right. Okay, and then one-to-one mapping, one-to-many mapping. So there is a mapping. You remember that the semantics performance or semantics meaning, and then design options, okay. Descriptions. So there can be a mapping, one-to-one or one-to-many mapping, one-to-many. Well, usually the design goes in this way. Many-to-one mapping or one-to-many mapping. If these statements are expressed as abduction is similar to designing, then the mappings become usually one-to-many. Right? Abduction is one-to-many. Rules define spaces of design, in terms of constraint, feasible regions, optimization. So once again, optimization problem is something like minimize some function. It can be weight or it can be cost, it can be any performance variables. Subject to and constraint. Constant is usually written as H or G or H. G usually is made of upper bounds or lower bound. H is something like equality constraint. X is a design variable. So for this problem, so applying 10 kilogram force, and then design variable can be diameter, length, or solidity, and then material, something like that. Right? And then minimize, say, weight or cost, right, to sustaining the force. So it can be permissible stress level when I applying to this 10 kilogram force. The material can sustain, say, 100 psi or something stress level. Right? So this can be 10 kilograms some force, something like that. And then once this is we call the formulation or optimization problem. Optimization problem means every part is written as an equation, formulation, mathematical equation. That is tough process. So this problem, when I say to you as a sentence, can be converted into mathematical equations like this one. Then optimization algorithm can solve that one. So give you the answer, the minimum weight type design. And feasible region and constraint and optimization and we'll see that what it means by feasible region. There are two. Okay. Right. And then producing design through interpretive knowledge. And there are also subsections of interpretation of design specification, design requirement of intended performance, design requirement, and interpreting design specification for problem formulation. Problem formulation can be like this one, formulation. So you're trying to make education, mathematical education out of them. So interpreting intended performance, right? Design requirement into equations, that is formulation. Plausible inference from design specification. Starting from here is something like probabilistic problem solving. And fuzzy reasoning, plausible inference from design specification, and also through constraint propagation is very similar to this constraint. This is called constraint. assumption-based reasoning. Also, some kind of uncertainties implied in here, fuzzy, plausible assumption. So, interpretation of design specification. There is an assumption that closed word assumption and also one-to-one mapping assumption. So to make it simpler and easier. But design usually not apply this one. Anyway, here the book is trying to. There are no conflict in the abductive form on knowledge in performance. No conflict among subgoals. There is assumptions, but we may not use this one. Design in real world. The design requirements are interpreted to produce a design description. Okay. Design requirement in this way. Abduction is right. Design requirement is interpreted to produce design alternative description. And this is suitable for selecting solution to a task. So among available catalogs. So I want to buy my smartphone. Then we can just visit a home shopping, internet shopping site, and then by evaluating these alternatives, I just select one. This is coming many times in when you're designing a real, say, car, airplane. Every part, not every part, but most of the parts should be selected among available catalogs. All parts. So specification, starting from step specification, we arrive at designing. And interpretive knowledge is used, but in the other way. What is this? So this is a expert system. General build, general expert system builder, and computer application research unit, Department of Architectural Science, University of Sydney. And Rosenman is one of the authors of this book, main author. And 85, how many years ago? 30 years ago. Right? And then this one is a system for selecting, sizing, and retaining the walls of the building. So expert system for a graphical window. There is some site, height, and elevation, and something like distance from between different houses, something. There is some kind of regulations or constraint, we say. And problem formulation. Optimization problem where conflicts are handled algorithmically. Right? There is a special algorithms called optimization algorithms. Many of them are available in the commercial market or open source. Right? You can use them. But the problem is the formulation. Required performance or objective function. We call this is objective function. This is a constraint function. Or required performance, intended performance, can be transformed into minimum cost or minimum weight. Translate the informal description of a problem into formal algebraic description. Right. I want to design a smartphone for Indian ladies. That is very informal description. Can you describe this requirement into formulation like this? It can be tough, right? It can be But anyway, that is requirement for the formulation in optimization. So that is optimization algorithmic knowledge for translating performance, required performance, into design description. Problem statement and then formal algebraic description. That is we call the formulation. And this is some simple supported beam, simply supported beam with the uniformly distributed load. We saw this many times in mechanical engineering or solid mechanics or material strength problem. And we call this is an I-beam shape section, I-beam section of this shape. And then we can make this problem same as this one, same as this one. Very similar to this problem. So we can formulate in this one. Many people already solved this one. And this is also canonical model of beam problem into mathematical model for the beam design problem. And they say minimize x, x2, x3, x4 subject to, this is constraint function. The over one is objective function, constraint function, and one is less than, this is greater than, right? Among design variable equations. Right? And there are design variables. And also, each design variable has also ranges. So this is also constraint function. And there is a continuous variables and there are description. Beam flange width, beam flange thickness, web depth, overall depth. And then after formulation, the solution can be found by algorithm quickly nowadays in this way. And then this is what? The solution, solver, right? Variables, objective, constraint, and model. So they are saying there is a model number of constants is 13, objective function is nonlinear and quadratic. The equation itself, nonlinear. The equation type here is nonlinear, right? x1 multiplied by x2, also x3 multiplied by x4, so it's a quadratic, second order. And then the solver and the nonlinear programming algorithm is being executed. And the program solves the nonlinear programming problem using the sequential linear programming method. This is one of the algorithms for optimization. They found initial feasible solution found. And solution process in process. And then summary of result. The minimum weight of the beam is this number. At this point, the decision variable is in this way. So it is solved. And plausible inference, if, this is simple rule, if A, then B. But additional one is plausibility. This is a probability. Probability of this rule is working. Right? Not always. Sometimes it works. Right? P means a support, plausibility factor attached to a rule. That is a real world case. We choose the hypothesis that has the highest probability given to the accumulated evidence. So when you chaining the rules several times, then the probability can be applied, right? Multiplied. Plausibility measure attached to any proposition. So we call this is again as a measure of belief or probability. And this is plausibility assigned to this rules. So flexible servicing requires then you need to have a crawl space or sloping site condition. So we need to have in this case, we need to have a raised timber floor for the house. We need to have a network linking evidential propositions and hypotheses. Sometimes we need to have a concrete slab on ground to build the house. How we prepare this platform floor? Sometimes we need to have a concrete, or sometimes we need a raised timber floor, right? Depending on this reasoning process. For the architectural problem, and this one is more simplified, the propagation of measures of belief from these problems, cases, different cases. So it's real calculations. And once again, this one is already shown to you last week. So uncertainty type has ambiguity, incompleteness, vagueness, randomness, and inconsistency. Among them is also probability. Fuzzy reasoning. Fuzzy is also kind of big area of research. In this case, this is a non-precision reasoning is working. Very similar, right? Probability. Want to reason with imprecise statement, but we want to convert them into mathematical equations to make fuzzy optimization things. So fuzzy logic, we call that fuzzy set or fuzzy logic. So one example is a linguistic variable, something like adequate, moderate, highly suitable, hot, sweet. But it depending on your subjective, depending on the person, right? Can you convert, say, this is heavy or light? How heavy? Can you measure it into a number? But depending on yourself, right? Baby or strong man, lady may count it differently, right? So we need to handle this kind of things in the real world, right? So sometimes we use this kind of idea, set membership function, to convert them into a mathematical formulation. Right? And so what is this? Inference network or rules containing fuzzy predicate. So adequate and moderate. This is requirement. The sentence for requiring building of a concrete slab building with highly desirable. This is also linguistic variables. Suitable, medium. Right. So we need to handle this kind of situation inside the knowledge-based system. Right. So set membership function or set is like this one. Right. So flat or stiff, the slide, slope, or heavy or light. Then, depending on the situation, we want to scale it into 10 maximum grade numbers and convert it into numbers. There is an idea behind this. So, depending on your measures, the numbers can be in this way. So you can, at the beginning, you can assume the shape of this membership functions. And then that applies to each linguistic variable. Constraint propagation. So constraint here, but not algorithm, but there is another way, is propagation. And constraint is what must be true, what must be satisfied in order for A to be proven. Right? And constraint propagation means transforming constraint into form that makes them more explicit. So it can be similar to constraint checking or constraint propagation. So requirements. For determining suitable color, so what is suitable? That is also linguistic variables. This one should be moved to anyway. Red like, yellow like, a cheerful. Yellow like means a cheerful. So both gives you a orange like, and that means suitable. So we can say orange like is suitable color. That makes linguistic variables are working. And similarly, the constraint checking. This one is constraint checking. So suitable checking, and then it can be melon, cabbage, and tomato. So melon is yellow. Cabbage is not yellow. Tomato is not yellow. So in this way, we arrive at this cheerful and correct. And then constant propagation. If you use constant propagation instead of checking, we can reduce the amount of search in backtracking necessary. So this is similar to previous one, and differing. Decision is made later until the last moment. We call this. So propagation constraint can lead. Sometimes it gives you a direct solution. Sometimes not. So constraint set gives you a design space. Similar to this idea of this one. Sometimes these equations, if this is a linear equation of only two variables, we can draw this kind of less than this equation, also less than this equation, so that we arrive at this feasible region. But because there is only two variables, but if you have three variables, then it can be a three-dimensional space, but there are many. Sometimes it can be 100 design variables in social economical problem. Then you cannot draw this one. But conceptually, you can draw multi-dimensional spaces. So final sample is trying to arrive at shape of the housing, but there is some constraint. Say the house must be next to the cell occupied by the garage. So garage should be next to the house. Pool cannot be next to the garage, and pool must be north of the house, and the pool must be north of the garage. Right? Pool must be north of the garage. That is requirement or constraint. And by using these ideas, we operating trying to, so garage and house is H and G, and then pool, right? Pool. So a house should be adjacent to garage, and pool cannot be next to the garage, and pool should be north of garage, pool north of south. So there is a available site, and there is an exclusion zone. Then we need to arrive at manipulating these constraints to arrive at this elimination of spaces, and then goes on to this way, optionals, and then the other options, and constraint of figure, and then probably this one is final. No? One more? Okay. So possibility of pool and garage and house is in this way. So there can be, this is an available site. I have a land of this way. And then it can be, solutions can be in this way. So there is elimination of possibility and reduced to the other. Sometimes the constraint defines only one single solution. In this case, there are several possible solutions. So solution space, we can say. Plausible, reasonable, feasible, reasonable. It takes a long time. Right? Assumption-based reasoning. And then the previous two approach for the problem of conflict in abductive reasoning. And we say there's plausible solutions and feasible reasons and constraint. And non-monetary reasoning was truth maintenance, deferring the solution on hold until the final stage. And this is it for today. Okay.